undamped forcing and resonance. So we're going to study the effect of sinusoidal forcing on an undamped harmonic oscillator. So undamped means no friction, right? You've got a mass on a spring sliding back and forth, undamped, which means that its solution will be sinusoidal, right? Or a center, because there's no friction to make the motion die out. So though most physical systems have some damping, if it's sufficiently small, the behavior of the undamped harmonic oscillator is still a good model. So the three-step linearity principle that we've been using, the solve Y homogeneous, find a Y particular, add them together, still works here. However, the general solution of the unforced equation doesn't tend towards zero. Like you're not going to have an e to the t, e to the negative t on each of your two terms for the homogeneous solution. And with no damping and no forcing, the solutions to the harmonic oscillator are periodic or sinusoidal, right? Sinusoidal or centers if you were looking at a phase plane, right? So if there's no damping and no forcing, it's just a mass on a spring, no friction, just keeps moving back and forth forever. But now we're going to think about what happens to this undamped harmonic oscillator if we add a sinusoidal forcing function. So meaning a force that has that's periodic, that is applied to the mass on the spring. So like you're just hitting it every so often, and so the timing of how you hit the mass on the spring is going to make a huge difference. So like if the spring is moving this way, like this, and you like hit it, like you're just going to mess it all up. But if you hit it with just the right timing, like if just as it's about to start heading that way again, you give it a boost, it's going to amplify the motion. So the frequency that you apply your forcing function is going to make a huge difference in what happens to your system. And when you just keep amplifying the motion, it's called resonance. And there are really cool applications of resonance that we're going to talk about. So one nice way to picture it is like when you push someone on a swing, like if you hit them at the wrong moment, you're just going to like make them, it's just going to be all jarring. But if you hit them at just the right moment, they go higher and higher and higher. Or double bounce on a trampoline. Yeah, I actually have a video of a double bounce on a trampoline to show you. Yeah, so if you add to the force that the person is bouncing on the trampoline with a certain frequency, if you add to their force at just the right moment, you amplify how far down the trampoline goes and then how far it throws them up. Yeah, pretty much, yeah. So we're going to consider what happens to an undamped harmonic oscillator if you add this sinusoidal forcing function. And the omega, right, remember that the frequency is like omega over 2 pi, right? It's that coefficient on t over 2 pi, or the period is 2 pi over omega. So the frequency, that omega, is going to make a huge difference in how that forcing function affects the harmonic oscillator. So I'm just going to apply my typical method for solving this using the 3 steps: find Y homogeneous, find Y particular, add them together. So first I'm going to try to solve Y homogeneous. Just replace the forcing function with a 0. So this says s squared plus 2 is 0. So s is plus or minus I root 2. So Y homogeneous, I'm skipping some steps here because we've been through this a bunch of times, and if you need to go back and review it and write it all out, you can do it later. I just want to make sure we get to the punchline here. This becomes k1 cosine root 2t plus k2 sine root 2t. So there's my Y homogeneous. And you can see it's just a sinusoidal because this is an undamped harmonic oscillator. There's no damping term, with which is the Y prime term. So it's just sinusoidal. It just keeps doing the same thing forever. There is not. Right. I left out the part where I like do all that stuff. So there's my Y homogeneous. Now I need a Y particular. And I could use complexification or lucky guess, where I would make my guess alpha cosine omega t plus beta cosine omega t. Or I could change this to an e to the I omega t and make my lucky guess, my guess for Y particular, alpha e to the I omega t, right? So this is the same process we've been going through. And I guess I'll write it out since it's new. You don't. No. You can use either method. Yes. Yes, this is a choice. So if I do complexification, I would guess Y. I'm using Y complex because it's not really the Y particular I'm looking for. Alpha e to the I omega t, which means Y prime is I alpha omega e to the I omega t, and then Y complex double prime negative omega squared alpha e to the I omega t. Then you plug your Y and your Y double prime into the original equation. There is no Y prime term. And find our Y complex. So see, I'll write this down. I've got Y double prime plus 2Y supposed to equal e to the I omega t. Put in my Y double prime. Put in my Y, which is alpha e to the I omega t. And then I got to solve for alpha. So basically, I'm going to factor out e to the I omega t, and I have negative omega squared alpha plus 2 alpha equals 1. So alpha is 1 over 2 minus omega squared. So that means that my Y complex, right, my guess is actually 1 over 2 minus omega squared e to the I omega t. I'm going to change e to the I omega t to cosine omega t plus I sine omega t. And then distribute. And my forcing function here is cosine. It was originally cosine. So once I distribute this, I'm going to grab which part, the real part or the imaginary part? The real part. So my Y particular is just the real part of this Y complex. So it's going to be 1 over 2 minus omega squared cosine omega t. So I know I did kind of fly through that, but I just want to get to the interesting part. So my Y general, remember, is your Y homogeneous plus your Y particular. So it comes out to K1 cosine root 2t plus K2 sine root 2t. Yes, thank you. Plus Y particular, which is 1 over 2 minus omega squared cosine omega t. So that is the general solution. Okay, so the homogeneous solution, this part is called the natural response. Right? That's what would happen in the absence of forcing, the natural response. And then this Y particular, that's called your forced response. All right, so what is the natural frequency of the system? So we look at the general solution, we just look at the natural response part. The frequency would be 2 pi over root 2. Make sense? 2 pi over root 2. Frequency is just the reciprocal of period, right? So in all your, we've always talked about period in all previous classes. Frequency is just another way of talking about the same phenomenon. It's just the reciprocal. All right, so what is the forcing frequency? So go back to the forced response. The solution, yep, the coefficient on t. Like if I asked you what the period of cosine root 2 t, yeah. All right, so in my forced response, the frequency would be 2 pi over omega, right? Because the coefficient on t is the thing that determines frequency. So 2 pi over omega. So here are some graphs of typical solutions for a couple different values of omega. So if omega is a half, you get this like weird periodic thing. And then when omega is 1, get a similar thing, just the amplitudes get larger. And when omega is 1.2, you get this phenomenon, which is called beating, where the amplitudes get big and small and big and small. Yes. Yeah. When omega equals root 2, you get a totally different response, right? 1.2 is very close to 2 pi over root 2. Oops. What did I do? Okay. So the amplitudes of the oscillations increase and decrease in a regular pattern. This is called beating. It's most evident when the frequency of the forcing function is close to the natural frequency. So you can see it most when omega is 1.2 because that's very close to root 2 over 2 pi. The terms with very close frequencies, when you add them together, they tend to either amplify each other or cancel each other out. And you can hear this when somebody plays 2 notes and one is just slightly out of tune with the other. You hear the volume seems to increase and decrease. I think I have to take this out.